Okay, now we are live.
All right. So, hello everybody again. Welcome, the official welcome. We're really happy to have all of you here, and we're happy to be part of the Digital Futures 2022 workshop series. So we titled the workshop a bio-inspired generative urban tissue growth and optimization workflow. And Uwe already introduced himself, so I will introduce myself as well. I'm Ridwan Kahraman. I'm a computational designer and materials engineer. My bachelor's was actually at Sabancı in materials science and engineering. And my master's was also at Northwestern University, also in materials science and engineering. So I didn't have pretty much any experience in architecture, but I always wanted to be an urban designer actually, and also an architect. So I did everything I could to kind of switch my careers. So that led me to doing a master's at the University of Stuttgart in integrative technologies and architectural design research. And now I work as a CAD engineer or a BIM engineer at Werner Sobek, which is a structural engineering company in Stuttgart. Can I get the laser pointer here?
I think right now, yes.
Okay, I can't find it, but it's fine. I'll continue with the mouse. So I don't know if all of you have seen the introduction to the workshops that was published, I believe, a month ago or so. There we shared our plan for the workshop and also some of the summaries, etc. So in case you didn't see it, I'm going to go through it quickly again. So basically, we divided the workshop into 3 days. The first day is introduction, which is what we're doing right now. And then we will do a short presentation on the definitions and talk a little bit about the history of simulations in urban science, and talk a little bit about the algorithm that we're going to use. And then we're going to get into Grasshopper today. So today we only have 3 hours, so we're not going to be able to finish the DLA algorithm completely. And then in day 2, we're going to continue with the algorithm and finish it up. And that's the part 1, which is the part that I'm going to be tutoring. And then Uğur is going to take over in the second part and talk about the optimization workflow, integrating anomaly with VLSA, and then doing the simulation and then data analysis. So yes, as I said, the part 1 is only finishing the DLA in Grasshopper. Yes, so this is what I mentioned. So this summary is again from the previous workshop, previous presentation that we did last month. So we're basically trying to generate urban structures from a process that is found in nature, which is the lichen growth, right? So these lichen grow in this kind of branching structure. And it's quite interesting that it somehow matches the growth of an urban system. And we're going to talk about the similarities later on as well. And there has been other research which used this kind of bio-inspired algorithms to generate urban forms. And we're going to talk about why we're doing this. So in the part 1, and hopefully the outcome of today is going to be, we're going to create a short script that's going to move points randomly around a single point. Once we're able to do this, we're going to add a few additional functions in there, which is going to make some of these particles stuck. And the sticking particles will organically create this kind of growth and this kind of form. So hopefully by middle of tomorrow, we're going to be able to have this. Then in part 2, we're going to plug this into the generation of an urban form. And hopefully at the end, we're going to have a few different urban patterns, urban fabrics, each of which is going to have their own fitness values and how well they fit into our criteria. So this is what we're looking to get towards at the end of the workshop. So to generalize and summarize our aim, 2 aims is the first is to generate an urban structure using a simulation method. And the second is to optimize the parameters of the simulation method to generate an optimal urban structure. A lot of you, it seems, were interested in the bio-inspiration part of this, the workshop. Bio-inspired and sustainable simulations, etc. And they're a bit off the trend these days, and everyone is really interested in this. So it might be good to define some of the terminology of what bio-inspiration means, because it comes with a lot of different terms. So let's first define what bio-inspiration is. This is taken from mostly from a paper from Speck in 2017. And basically he defines it in a few sentences. So one of these is technical solutions having a biological idea generator. And then he says, in general, bio-inspired design takes place on basis of visual, conceptual, and computational inspiration. Utilizes similarities between nature and design challenges to bring inspiration to designers. And also, finally, transfer of algorithms from evolution, natural morphogenesis, or others. So one of the examples that he gives in the paper is the invention of reinforced concrete by Joseph Monnier in 1855. So apparently, historically, Joseph Monnier looked at plants, and he realized that in plants, there are fibrous structures which are making the plant stronger. And then he decided to test it out in basically a product that he wanted to make for the industry. And he came up with the reinforced concrete that we all use today. One of the things that's important here is that it seems like he didn't really know how the fibers were functioning, but he tried it out anyway, and it worked. And that's an important distinction between bioinspiration and biomimetics. According to Speck, the difference between biomimetics and bioinspiration is that in biomimetics, the extraction of principles from biology is necessary. So you have to really understand what's going on and why the biological role model works that way in order to then extract that principle. So the first definition is technical application developed on the basis of a transfer of knowledge from a biological concept generator. So one example for this is Velcro. We use this pretty much every day. The Turkish word for it is cırt cırt, which is kind of funny. So basically this guy he was walking around and he saw that these seeds would get stuck into his socks, and he was trying to understand what was going on there. So he really looked into why it was that these hook-shaped things would catch onto this wool. And this middle step is really important. He extracted and abstracted the working principle, and then he brought it back into the product. So that's the step that's missing in bio-inspiration, right? So there's no real understanding here that's going on. And I just wanted to show you this mostly because we have to be quite careful when we're using these terms. There's a lot of terms that I'm not going to explain here. So there's biomorphic, bionic, reverse biomimetics, biomimicry, sustainability. They all mean slightly different things. And if you're interested in this, you can read this paper by Speck et al., where they explain what each of these terms are. One other thing I wanted to talk about here is the sustainability idea. just because something is bio-inspired doesn't necessarily mean that it's sustainable. So that's another thing where we have to be careful when using these terms. And especially those of you who are starting out in your careers and you're looking at papers who are claiming something is sustainable just because it's bio-inspired, you have to be careful that it might not necessarily be so, right? Because sustainability requires an additional analysis. And that's kind of why we are also adding the Volosé, right? Because we are doing something bio-inspired, but then we're also optimizing it to make sure that it fits into the criteria that we are selecting. This could be sustainability, or it could be, square footage, plot size, whatever it is. In terms of what we are doing, the reason why we called it bio-inspired is because we're using nature as an idea generator, but not necessarily extracting exactly the working principle from it. So it fits more into the bio-inspiration case rather than the biomimetics case. With that said, now we can go on to explaining what DLA actually is. So DLA is an agent-based simulation method. Its actual name is diffusion limited aggregation, and it simulates branching structures found in nature. These branching structures are not only in moss or lichen, but they also occur in other places as well. For example, if you go onto Wikipedia and write diffusion limited aggregation, you get this image, which is the dielectric breakdown of a block of polymer, for example, and it creates a similar structure. One other term we want to define here is urban morphology, right? So those of you who are studying in the urban field might already know. So the definition is the study of urban forms and of the agents and processes responsible for their transformation. Urban form mainly refers to the main physical elements that structure and shape the city, urban tissues, streets, urban plots, and buildings. And this definition comes from Oliveira's book. So the question here is, what does DLA have anything to do with urban morphology, right? What does growing moss have to do with an urban plot? And I want to get into a little bit of the history of why these agent-based simulations are even used in architecture, which might help us answer this question and which might help clarify in your minds why we're actually doing this. And I'm going to start with the complexity science, right? So basically, complexity science is a branch of science that became popular in the 1960s. Before complexity science, we had basically linear systems. In linear systems, outcomes are predictable. We all learned this kind of science in our high schools. Basically, you have, for example, this is a linear system, right? You have a weight, you put the weight down, and then the spring moves a certain distance. You always know exactly how the spring is going to move, right? It depends on the stiffness of the spring, and it depends on the weight. So this is kind of what is called a linear system. And Jenks called this a modernist worldview, right? Where everything is predictable, everything is linear, and you can do science and you can get somewhere. Now in the 60s, things started to change a little bit, right? People started to find areas in nature which are not that easy to understand. So these are called complex systems or nonlinear systems. Outcomes are somewhat predictable in the overall pattern, but they're not exactly predictable. And small differences in initial conditions cause big differences in outcome. And Jenks called this the postmodernist worldview, or related to the postmodernist worldview, right? One of the examples of this is weather patterns, because we can never really predict what's going to happen to the weather. We can kind of predict in the next few days, but we can never predict, the next month. And according to the linear systems idea, we should be able to predict it, right? If we know exactly where it is, then we should be able to predict what's going to happen next. But we can't, because just slight differences make completely big differences in the long run. And this is, in popular culture, it's termed the butterfly effect. And this image is actually generated using Dolly. It's become really popular now. I wrote butterfly effect and saw what comes out, and it was kind of nice, so I put it in here. But basically the idea behind the butterfly effect is if a butterfly makes some sort of wind in some part of the world, then that wind is going to affect something small, and then that's going to affect something bigger. And maybe in 1 month, you're going to have a hurricane somewhere else in the world. The idea is you never really know what's going to happen in the future. Two important ideas that came with this thought process is self-organizing systems and emergence. So self-organizing systems, the definition is, it is a process where some form of overall order arises from local interactions between parts of an initially disordered system. So this is from Wikipedia. And emergence, also very similar idea. A system as a whole has properties that its parts do not have on their own. Oops. Yes, so this is what I wanted to show here. So to explain what self-organizing systems and emergence are, you can look at the GIF here. So this is a GIF from National Geographic. It's basically a bunch of birds that are flying around in a certain pattern. The point here is that this overall pattern is displaying certain properties that the birds themselves don't really have, right? So it's self-organizing in that the overall order arises from local interactions. And researchers have found that it's very difficult to actually model the overall form of these birds. It's much easier to model the agents and then let the agents themselves model the overall form. And that's what emergence basically is, right? You model these points, and then in the end, the interaction between these points is going to create a big pattern that you're actually trying to look for. Yeah, so the question is, why is this important for architecture, right? And the answer is actually very important, because the architects were going crazy about these ideas in the 2000s and in the 90s, because suddenly there was a lot of new ideas, a lot of new possibilities. And we already talked about Michael Weinstock slightly. So he actually has an entire book just on emergence. And he's also an architect and a professor of architecture. Charles Jenks is a very important figure in postmodern architecture. And this entire book is about how complexity science is changing our worldview and how we need to do architecture differently now that we understand things better. Here's another book about emergence, and the subtitle is The Connected Lives of Ants, Brains, Cities, and Software. And the cities part is, of course, important, because now that we have these ideas ready, we can also try to understand the city a little bit better. Researchers for a long time understood that the city is very difficult to model, and it's also very difficult to predict, because there's a lot of actors and a lot of boundary conditions. So it's very difficult to model a city, and it becomes more understandable if you think of the city as a complex system as well, that it is also a form of emergence, right? And there's researchers who have done exactly that. So Michael Batty is one of them, and he's one of the people who has been working on this the longest. His goal, summarized from Oliveira, he seeks to understand the spatial structure and dynamics of cities as complex emergent phenomena in which the global structure develops from local processes, right? So this is exactly what we talked about in emergence. The global structure arises from the local processes. And he used this idea to model cities and wrote an entire book about it. And this book is like a thick book. I remember trying to read it, but I never I never finished it because it's long. So it's called Cities and Complexity, Understanding Cities with Cellular Automata, Agent-Based Models, and Fractals. And the entire book is basically about using these small-scale models and agent-based interactions to form the growth of the city, to model the growth of the city. He is still in UCL, I believe. So he's still doing research. And if you're interested, definitely check out his books and papers. Another example I want to give here about this approach being used well is Bill Hillier and Julian Hansen and the book Social Logic of Space. And if you're studying urban sciences, I assume, I mean, you might already obviously know this and have read this. So this book is about the relation between the local rules and how these local rules lead to global town formation, right? So they basically went to a lot of towns in Europe and found out that the towns had a structure that was quite similar to each other, right? So it had a group of buildings that are stuck together, and it had a ring of roads or empty space that is flowing around these structures. So they tried to understand why this was happening. Why is it that most of these towns display this kind of structure? And how do you model this? Like, how do you understand the growth of this? And they decided to use a model that takes advantage of these local interactions. So they made an agent-based simulation. And basically, each agent is an open closed cell couple. So if you look, can you see my mouse? Ah, perfect, laser pointer. Okay. If you see here, these are the agents, right? So this A is a building. B is a dot, which represents an empty space. And C is this couple. So every building is attached to an entrance and an empty space, right? So the only rule, is that every new empty space must be connected to an existing empty space. And then you just randomly place them together. And this simple rule, this one rule, is enough to create a town structure that resembles existing town structures. So it's really interesting how a very simple, small rule can create something that you can actually observe in the real world. Now, it might not be that this is the actual rule that people use when building the town, but it's just a good way to simulate what's happening and a good way to simulate the growth of the entire town, right? Finally, this is another paper that also really inspired this work. Is from Reinhard Koenig. So he took these ideas and tried to create different urban forms using these simulations, right? So he first identified 6 morphological patterns. These are what you see here. So I'm not going to get into the patterns, but you can kind of see how they're all slightly different. And you see these overall around the world, right? So you have, maybe this looks like somewhere you would see in the US or in the Americas. This looks like something more organically formed, etc. And then he used DLA and he used cellular automata to generate these structures organically using a simulation. And that's what also we showed in the summary. And this is also the algorithm that we're going to use. Although here there's a difference. He used these DLA structures as a road network, and we're not going to use them as a road network. We're just going to use them as a kind of like a template to build the city on, or the city form on. So why do we need to use biological role models? Why is it bio-inspired, right? If we can just use agent-based models. The answer is because in biology you actually have a lot of processes that are similar to what we're looking for, right? So we need a method that simulates organic complex growth, and a lot of biological structures show exactly that. They show organic complex growth. And the snowflake is actually also a very interesting example. So it also has a branching structure. And it could also technically be simulated with something similar to a DLA, right? And then here on the right, you have termites nest, which is also very, very complex and very organic. And of course, you can also use Grasshopper to simulate termites nest, but that's for another day, maybe for another workshop.
There to sign up next year.
Yes, exactly. Okay, so that's kind of the story of it. I think maybe one last thing to say is the answer to this question. So why do we use biological role models to generate structures? Another different answer could be it's because it's very difficult to model them in any other way, right? It's such a complex system. When you accept that the city is a complex system and it's difficult to model and difficult to predict, then the only way to do it is through bottom-up approach, right? So that's why a lot of these researchers go through the agent-based modeling system. It's because it's difficult to model as a whole. Yeah, and it's just that the biological role models provide some of the best solutions to this problem. Yeah, let's leave the references up for a few seconds, because these are really nice papers and books that you could take a look yourself if you're interested in, the ones that I cited in the presentation. Yeah, especially Michael Batty's and Bill Hillier's and Julian Hansen's books are very, very interesting for this kind of topic. Any questions? Okay, then I will keep going. Now that we have the kind of the story out of the way, we can talk about how to do a DLA script. So a basic overview of what happens in a DLA script is we have a starting center, which is shown in blue, right? So all of the particles that are not moving are shown in blue, and all of the particles that are moving are shown in red. So these particles, these red particles, are performing a random walk, which is basically, it's actually a scientific term that means it's randomly moving around, right? So there's nothing affecting it, basically. The second step is if one of these particles gets close to an existing particle, then it will get stuck, so it will stop moving. And it will become a starting center as well. So then if another particle comes close to it, it will get stuck as well. So then you reach a final configuration with these red particles sticking to, you know, all of the other particles, and basically it just grows, right? So the algorithm itself, how it works is just as I said. So the first thing you have to do is you have to move the walking particles. Every time the simulation runs, it has to move particles, and then it has to see if they're stuck, and it has to change its property from being stuck, from moving to being stuck, and then you just repeat the loop. So what we're doing is basically we're creating this loop that's going to keep running until a certain property is reached, which is going to be how big the structure is. We don't want to just run forever, right? And this is what we're going to be working on basically for the next 4 hours or so, including tomorrow. Uğur, can you check the chat every once in a while? Is there something there?
Yes, we have a question. I didn't want to interrupt you, but
okay.
Now that you stop, I can say that. The question is about Sana Rastegar is asking, I hope this is the correct pronunciation. Could we say L system a type of DLA? This is the question.
L systems are different from the DLA as far as I know, because L systems work with a specific pattern that gets repeated over and over again, right? So technically L systems are not even an agent-based modeling method. as far as I know. I've never worked on L systems, but I know that it's a pattern that keeps repeating itself, right? So no, I think DLA itself is specific and different from L systems, although L systems are used as well to create these branching structures. Thank you for the question, though. So we know what DLA is now, but one thing I wanted to highlight here is this simulate idea, right? So we are simulating branching structures found in nature. We're not actually doing what natural processes are doing. There's no, particles going around and sticking to the stuck particles. And of course, we all know that, right? We know how it grows. It grows through cell division, etc. But it's important to highlight here that what we're doing is a way to simulate what's actually happening in nature. So it's not necessarily exactly what's going on in nature, right? Which is one reason why it's not biomimicry and it's bioinspiration. Right. So here I wanted to show a version of this work that we did for our master's program at the University of Stuttgart. This was a class on coding. It was a class on Python and digital design. And basically we did this DLA algorithm using code. And using code gives you a few different possibilities than just using Grasshopper. And one of the things that we did, for example, so we have a bunch of input variables here, stuff called sun, moisture zone, jerkiness, etc. And these things, for example, change the way this DLA algorithm is growing. It has this exact same system, exact same algorithm, but the difference is we made it into 3D, which after this workshop, you could also try doing on your own as well. So we're going to stick to 2D for now, but you can convert this into a 3D system. In this case, what we did is, for example, if there's a sun, the growth goes faster in that region. And that's basically happening because we said every time a walking particle hits a stuck particle, there's a certain probability that it gets stuck. So it doesn't always get stuck. And this allows you to increase or decrease the properties, decrease the probability depending on where it lies. If it's close to the sun, it's more likely to get stuck, so it grows more. If it's in the moisture zone, it likes the moisture, so it grows more, etc. And our final result was this. So we basically used the DLA algorithm to create jewelry. So this was a pendant, a ring, and then we 3D printed it, and maybe I can show you later the actual 3D print of it. So with this workshop, it's kind of, I find it nice that we converted it to a Grasshopper algorithm, because Grasshopper is much more accessible than coding, and you don't need coding experience to actually do this. At the same time, it allows you to understand how the algorithm works, the steps of the algorithm, so that if you do want to code it, you can code it easier because you'll have a better understanding of how it works. Yeah.
Recording.
Okay. Yeah.
You can keep going. I think just one mic pop up and
okay.
closed.
Okay. Yeah, welcome though. I think it was someone who joined. All right, the workflow overview. So looking at the bigger picture of what we're going to do in both parts. So we have our DLA algorithm and we have our inputs to the DLA algorithm. These are what we can change with our sliders. These are our parameters. And these are basically the sticking radius, which is how big of a circle you have around stuck particles so that other particles are going to get stuck. So if you look here, it's the size of this circle. So if you make it bigger, the points are going to get stuck much faster, right? Or much further apart. So you're going to get a completely different DLA structure. You're going to get something that's branching differently. Then you have particle speed. So self-explanatory. Starting configuration, we're going to talk about, so I will also skip that. And then we have end size. So how is it going to end? Let's say we have 200 or 300 stuck particles, and then we decide to end the system. And then the DLA algorithm will spit out a nice configuration of particles. And we call this the stuck particle configuration, right? And then in the second part, you're going to focus on this part, which is urban tissue generation. So using the stuck particles, you're going to generate an urban tissue or an urban fabric. And then you're going to optimize this urban fabric according to certain fitness values. And that's where the Vol-SA comes in. So this is going to be the workflow that we're going to run. We're going to generate an urban tissue, we're going to optimize it, and we're going to generate new structures that are more and more optimal until what we want comes out of the simulation. Okay, so it's time to get into Grasshopper. Should we give a short break?
We're almost in an hour. I don't know. It depends on the participants. If they want, we can give a short break, like 5 or 10 minutes. But yeah, it really depends on the demand that we have. So what the participants thought? Do you want to have a small break before getting into practicing? We have one no from the
Maybe
chat.
5.
5 minutes. Okay, maybe
let's do a 5.
Yeah, 5 minutes would be nice. It's a very early morning, so it could be nice to
get a coffee and come back, guys.
Okay, then let's say 11:05.
Yeah.
Okay, so 7 or 8 minutes break. Okay, then see you. So I'm back as well.
So how many people do we have? 14 people, nice, okay.
So we can say that we catch the number that we were expecting in the beginning.
Yeah, we were going for like 15 to 20, and then it turned out 25 people wanted to join.
I hope that everyone gets the email, because at some point there has been some confusions. But yeah, we did our best to reach anyone. So I think some of the people also have been working, because some of you ask me if we are recording and uploading the video because of the schedule, and the answer is yes. You can see we're already recording, and we are going to be uploading hopefully at the end of the day, but in case we cannot upload it at the end of the day after the workshop, we're gonna send it in anyway.
I just saw Louis. By the way, thank you for switching the main, Louis, right? That's what you said. Thank you for switching the main language to English and make this workshop available to a larger audience. Yes. So the initial idea was to hold the workshop in Turkish. But then, I mean, we realized even if you look at the participants now, most of the participants are not Turkish speakers, so it made sense to switch it to English. We're also happy to have more participants, so of course, you know, it wasn't a problem for us.
Yeah, also thank you for asking this opportunity. Yeah. It's always better to define what you're looking for by yourselves.
Yeah, exactly. Should we start?
I think yes, it's already passing 6, so I think we can start.
Okay. So, Grasshopper. If we're going too fast, please tell me to slow down whenever you want. So I'm going to show a few things on the slides, and then the rest of the today and tomorrow, I'm going to just be on this screen with the Rhino on this side and the Grasshopper on this side. Stop me whenever you want. You can just ask the chat in the questions, and we can explain things further. If you are unable to catch up at certain points, we have prepared some checkpoints. And if you go, do we have a link to the?
I think we didn't share the drive yet, but let me quickly find it and put it on the chat.
Okay. Yeah, we're going to share the, maybe also at the end of the day, we can write an email, because the people who are not here can also use that. But let me see if I can show you what I'm trying to say.
Also, it would be nice to quickly explain the general structure of the drive, what we have. And
yeah. Would you like to do that?
Yeah, of course. So as you can see, we have 3 clusters stating the days. So at the end of each day, we're going to be uploading our progress and also the recording of the lectures as well, hopefully at the end of the day, as I said. And then we have a material section where we are sharing some of the Grasshopper scripts. As Rudvan mentioned, we are going to be, we already have, I think, the scripts, right? Okay, this is not the one. This is the one that is necessary for the second phase, but we can upload it here, and then you can reach the checkpoints as well. I think
let me do it now.
Yeah, okay.
Let me upload it.
Okay. And we have a Q&A folder, I guess, which has the Excel file that some of you already fill it, and then throughout the workshop, we're going to also use it for further intentions. So it's pretty much straightforward. I just wanted to quickly summarize it. And I'm in the meantime, I'm going to share the link so everyone can be a participant to the drive as well.
Yeah, so in the checkpoints folder, for this part, we have these 7 checkpoints. So if there's any part which you are missing, which you weren't able to do the Grasshopper part fast enough, you can stop doing the Grasshopper, just listen and watch me do it, and then you can just download this checkpoint and continue from there. So if at any point, I will let you know where the checkpoints are. Yeah, we'll just share the drive so you can find them in this link.
I want to underline what you said. Please don't try to catch everything in the practical part and get a stress. You can even ask, like we are going to be having a Q&A section at the end of the workshop series. We can discuss everything there. Otherwise, also, apart from everything, you can directly ask us also outside of this workshop as well. So no worries.
Yeah. Okay, so let's talk about some useful shortcuts in Grasshopper. It's really interesting that a lot of people who use Grasshopper actually don't know these shortcuts. And I wanted to quickly talk about them because people then ask when I'm doing them, how I'm doing them. So when you're clicking on a component, Alt, Shift, and Control do a lot of different things. And I will show this on the Grasshopper screen as well. So let's try the first one, right? And you can try this as well. So if you click on a component and click, while you're dragging it, click on Alt, then you get this plus icon, right? So this is true in all modeling software. If you press, or even in Google Docs or whatever, if you press Alt, you will make a duplicate of it. And I use this all the time. If I have a curve on screen, I will never search for a curve component because it takes longer, right? I just do this and it just brings me many curves. So you can use this this shortcut to do to make your workflow faster, and I will be using it quite a lot. Shift click on wire entry, right? How can I show this? So if I do not shift click, I actually don't remember how to show this anymore. We will show it when it comes up, but you probably know it anyway. Control click on wire entry is to remove wire. This is also important. So if I have this wire, I want to remove it. If I press Control and hold Control, then I get this red minus wire here. And then I can just do this and it removes the wire, right? So this might also be useful. And then the most secret click combination in Grasshopper, which, okay, obviously it's not, but it's quite interesting. Control Shift click on wire entry, right? So this is useful when I have 2 wires coming on here, right? So I press Shift, I make another wire. I press Shift, I make another wire. And then I press Alt. And let's say I disconnect these, right? Disconnect all. So now I want to move all 4 of these wires into this, right? And the fast way to do this is I click Control, Shift, and then I take all of them. And I put them in here, right? And that is very cool because you can, I mean, it allows you to do all, it just makes everything much faster, right? So definitely use this, use these tools, these shortcuts. It'll make your life easier. Of course, it takes a while to get used to, but you know. So those are the shortcuts. Now, useful tips, right? In big Grasshopper files, I'm just going to make this full screen. In big Grasshopper files, it's very nice and easy to understand what your code is doing if you group them. So here you can clearly see that there's two main functions, right? Two main blocks of code. And if you do it like this, it becomes easier to understand for yourself. It doesn't matter for anyone else because most of the time Grasshopper codes are not shared. But for you to understand it in big codes, try to group them. And I also like color coding my functions. I mean, it's up to you, but I just like doing it. It makes things easier. For example, I said here, blue is stuck particles, red is moving particles, right? So here, when I look at this and I see this blue and I see this red, I already know before clicking on them what they are, right? So it makes everything much easier. I don't have to think about, oh, where's my particle? I don't even have to see the name, right? So it makes it much easier. So I would recommend this. And this third one is also important. It's to make inputs and outputs clear. Any of you who has worked in coding knows that inputs and outputs of functions have to be clearly defined, right? So, but if you use this in Grasshopper, it's also really nice. So if I have a function that takes in, 4 curves and spits out 2 curves, for example, I will probably group this like this. And then I know, and if you use these arrows, it will align them as well. That's also interesting. If you click all of them, press the arrow, press this, and it aligns them, right? Do the same here. And now I know I have 4 inputs, 2 outputs. This is a function, right? So it's very clear what it is, what it's doing. And then maybe I name it something and it's obvious what it's doing. Yes, let's keep going. Clustering, right? I don't know if you have worked with clusters before, but it makes things quite clear as well. So if I have these 2 functions again, if I cluster them into this box, then it will just make the description much shorter, right? So this is also highly recommended. A trick when you're using clustering is whenever you go into this curve, you can right-click this curve and you can rename it something, right? So I will put curve 1, for example, here. And then I will right-click this and I will put curve 2, curve 3, and then last curve, right? And then I will, for example, have inputs. This is just an example. Don't worry about anything, the orange stuff. So when I click all of this and I right click and I say cluster, right? It becomes a function. And the important part is that because I named the inputs and outputs are named here as well in the cluster. So it makes it easier for me to know what is curve 1, what is curve 2, and this, I mean, obviously here, of course, it's 1, 2, 3, right? But you get the idea. And here I didn't name them, so they're all curves, which is not very self-explanatory. An additional thing is if you go in here, and I think I have it on the slides as well. If you right-click on any component in Grasshopper, you get this option here to use application setting or to draw the name, right? And I will show you here as well. So if I right-click on this, I go to this paint bucket icon here, and it's on use application setting. I click on it, and then now it's drawing the name because it changed to text. It says always draw name, right? It depends on what you're doing. Some people like to use, where is that? Display draw icons. Some people already work with curves like this. Some people like to draw icons. I like to draw icons. So this is useful for me when I want to switch between text and icons. And this is very helpful when I'm naming clusters, right? I don't know what this icon is. And if I change it to name, it says cluster. So this means nothing to me. But if I right click, change the cluster name to 4 curves to 2 curves. And now when I look at it, I know what it's doing, right? So yeah, that's also a nice little hack to know. Yes. Okay. Those are all the tips, and you will see me use them throughout. Let me also put the bifocals here.
Also, one thing that is really cool, you know, when you click Control and Alt and point the component, it shows the location. Sometimes it's, you know, we find one component and then never find it again.
Yeah. So, for example, let's say I have an offset surface here. I don't know where it is. Control Alt click, and then it automatically shows me where it is. It's in surface, it's in utilities, and it's here, right? Yeah. Okay. So we can start with the first task now, right? Task 1. We need to move particles randomly. We need to do this. Random movement of particles. Okay. So you have an empty Grasshopper file, right? I will first talk about anemone because we're going to be using loops. So if you go to anemone, you see here in the first tab, you have loop end and loop start. So let's start with loop start. Let's put it here. And then let's put the loop end. And these two have to be connected. So loop end has to be connected to loop start. And then let's put this here. So whatever we're going to be doing inside this region here. To create these random moving particles, before even creating the random moving particles, I want to create one particle that's going to be stuck at the center. That's going to be our center point, right? So let's say, let's go to search. Let's write 0, 0, oops, 0, 0, 0. And it gives you a point at 0, 0, 0, right? Then this is my stuck particle. So I will group this, which is Control G, and I will color it in blue, just so I know what it is, right? Blue color. Okay. Then I need my moving particles, but the moving particles have to start from somewhere. And because we're working on 2D, it makes sense to have a circle, which is going to have a lot of moving particles start at the circle, and they're just going to start moving randomly, right? So I'm going to start drawing a circle. So I will write circle, and I get circle CNR. I click on that. Center is automatically, I believe, 0, 0, 0, but we can just, again, put the 0, 0, 0, and we can put center. Normal is automatically Z, don't change it. Radius, let's make a slider. Let's just say 35 for now. And let's put radius, okay. So we have our circle here, let's zoom in. Now, we want particles to start from this circle. A nice component here is divide curve. If you just write divide, it comes up. And if you're wondering where it is, if you Control Alt click on it, you see it's curve, division, divide curve. So we have a bunch of particles, right? And then we have the count, the number of segments. So let's start with 150. Now we have 150 points on the circle. I will rename the sliders so it's clear what it is. So here I will name it, let's see, number of particles. And here I will name. Then the point is to move these points. The idea is to move these points in a random direction, right? But all of them have to move in different directions. So I'm going to create a function like I mentioned in the slides. Basically what I'm going to do is have something like this blue one, right? So what are my inputs? My inputs are walking particles. So I'm going to write point. I'm going to get a point, right click on it, rename it W particles for walking particles. Right click, get the sky, walking particles. And then I want to move these particles. So I click on move. And the move component is asking for a motion vector, right? So I need to create a random vector for each of these particles. So we can use a random component here. It's going to create a random speed for us and a random direction for us to move the particle. The problem is, of course, there needs to be an input of how big the number is going to be. So I'm going to create another input here in the very beginning. I'm going to create a slider from 0, well, not 0, let's do 3 to 5. And I call it particle speed. I will create a domain, construct domain. And then basically I will connect this to domain end. Now what I'm trying to do here is I'm going to try to construct a domain from -3 to 3, because it could move in all directions, right? It could move in 3 in one direction, -3 in the other direction. So I want a domain from -3 to 3. So how I'm going to do that is I'm going to use a negative component. If you just write neg, you have negative. You put this here, domain start, domain end. And now if I get a panel, it's very useful to have panels. If you put two times slash, you get the panel, domain -3 to 3. And I want to plug this into my range. So now let's see what random number I have. Okay, it's doing what it needs to do. However, it needs to make many random numbers, right? It needs to make as many random numbers as I have particles. So I need to figure out how many particles I have here. So I'm going to write length. And I have here list length, measure the length of a list. I will use that, length, length. And I have 150 different values of speeds for each particle, right? Okay, now I need to create a motion vector. How can I create a motion vector? I say vector, let's see what comes up. I'm not getting what I'm looking for. I know it is, it's XYZ vector. Yes, this is correct. So I create an XYZ component. Now the issue is, if I just plug in these numbers, then my X and Y are going to be exactly the same, right? But I need a different Y and a different X because I want to move, I want it completely random, right? So this means that for each particle, I don't need one random value, I actually need 2 random values. So that's why I'm going to take this length and I'm going to multiply it by 2. If you just write multiply by 2, you get multiplication. And here, if you right click, you already see that it has 2 in it. And my result is 300. And now I have 300 random numbers. Is the speed okay? Is this everything fine?
Maybe once in a time you can stop and recap everything, and thus we would be sure no one is missing anything. And of course, if there is anyone who is getting hard time to catch it, please let us know.
Yeah. Okay. Here, there's going to be a bit harder, like a bit more complex thing that I'm going to be doing here. I'm going to remove this components. Now I have 300 random numbers and I want 2 per particle, right? The way I'm going to do this is I'm going to use partition list. Partition a list into sublists. I put this in here and I say I want size 2 for each partition, right? So I get a panel //2, enter, size is 2. Let's see what I have as an output. We asked you in the email to take a look at grafting, right? So, and grafting and tree structures. So basically what we have here is a tree structure with 2 points per branch. This is exactly what I want, because I want, for each particle, I want 2 values, right? So if I go to list item, this allows me to retrieve a specific item from a list. So basically, if I have 2 items on this list, I will retrieve item number 0 because my item index is 0, right? So this is the first item that I have on this list. So I'm going to plug this into the X component. And then I click on this plus value, and this allows me to get the second item from the list. And I plug that into the Y component. So now what I have is 1 vector per particle here. Yes. I hope that's clear. Now, if I want to move each of these particles with each of these vectors, then technically I have to put the particles in here into geometry, and I have to put this vector into the motion, right? But I don't want to do that just yet because of the tree structure. Here, if I look at this vector, I have a tree structure with different branches, right? Branch 0, branch 1, branch 2. And here, I have 1 branch with 150 particles. So if I plug this in right now, it's not going to work because it's just going to move all of these with the first branch, because that's how Grasshopper works. It goes branch by branch, right? So the only way I can move all of these particles with all of these vectors is if I have a tree structure with these particles as well. So how can I do that? I will alt click on this. So I will connect this here. So I have W particles, right? I will right click on this and I will select graft. When I do this, I have particles in each branch, right? Which is exactly what I have here with the vectors. I have every branch has 1 vector, and here every branch has 1 particle. So now I'm almost ready to put these vectors together with these particles. However, there's one problem here, right? Unfortunately, for reasons that I don't really understand, every time you do an operation, in some operations, Grasshopper adds a 0 to your branches, right? So if you look here, this is a tree structure with a depth of 3 branch levels, let's say. So we have 0, 0, 0, 0, 0, 1, etc. But here we have 0, 0, 0, 0, right? So this is going to create a problem if I put both of these things into this move component. It might create a problem, let's say. It's not necessarily going to create a problem. So what I'm going to do is I'm going to right click on this move component here in geometry. I'm going to select simplify. And in this motion, I'm also going to right click and I'm going to select simplify. When I do this, so if I actually get a point component and I click simplify on it and I connect it, then you will see that all of my trees have become 0, 1, 2, 3. So there's no 0, 0, zeros, there's no 0, 0, 1s. I really like working like this because it makes everything clearer for me. So this simplify button is going to be used for that. It can create some problems, but for our purposes, it's not going to create anything. So now that I have my simplify here, I will plug in my particles, plug in my motion, and voila. To make things a bit clearer, I would select all of these things and maybe middle mouse click and press this blindfold guy, this guy with the blindfold. It will disable the preview. So then you only see what you have in this lighter color component, right? You don't see any of these other guys. Yeah, so if I turn this on, the particles looked like this, and now they have all moved randomly in a random direction in a particle speed of 3. If I do 4, if I do 5, they change, right? They move differently.
So maybe here could be a nice spot to ask if anyone has reached to that level, or are there any difficulties that you are having with your screen? Because we started getting into summer, and
yeah,
we would like to know how many of you have reached to that point as well.
Maybe I have a question. Half of the points generated on the circle are not randomly moving on my
if I may, it's because you are missing the number 2 on the multiplication, I believe.
this.
Yeah.
Can you, where is it? On this.
Right now on the screen, you can see in the multiplication, we had number 2, but it wasn't visible. So maybe you have missed that part, as Louis said. Louis was right. I don't know. I heard someone's speaking, but anyway, or if it's not working, you can also share your screen and we can have a look at from your canvas as well.
I'm gonna check the multiplication just a minute.
What about the others? Does anyone have any other question, or did you guys?
I do have a question, if I may.
Mm-hmm.
Sure.
I believe, but I'm not sure. Would it be possible to use the populate component instead of all the components that you're using just to jigger the points? I mean, if you use the populate component, you will have a list of points, right? And you could use that list, the vectors as a translation vectors, right? And for example, if you input in the region, if you input just a rectangle, a regular rectangle in the input region, mm-hmm. You will have a bunch of points ranging from -1 to 1 in the XY direction. I mean, I'm sorry, I'm not really good at this explaining in English. Can I share my screen maybe, or?
Mm-hmm.
I don't know how to share my screen. Where is that?
I think you're all allowed to share in the left down part. You should see a button in the Zoom interface.
Yeah, I'm sorry, I don't know.
It's like a screen with an up arrow in the middle of it.
You say left button.
In the, I mean, I'm not sure if we have the same interface. That's why I'm a bit hesitant to direct you. I'm just trying to check the properties, if participants have the equal rights, but it seems okay. It says.
Okay, I don't want to waste your time, so I'll give up on that. And just my point was, I believe, but I'm not sure. I believe that you can use the output of the populate components and use it as translation vectors for the points. It's just that I think it's a bit simpler if you just use the populate component and you use the output of the populate components and you input it in the translation of
I see what you're saying.
vectors.
Yeah, I see what you're saying. No, that's quite smart actually. You can do that. Yeah, I think so. You just need to give the
to input just a rectangle, normal rectangle.
Yeah. No, that makes sense. Yeah.
Sorry about that.
No, it's really nice. I mean, it's like Grasshopper is such a cool tool, right? Like you wouldn't necessarily be able to do it in Python unless you use the Rhino interface populate 2D command or something. But in Grasshopper, you can do all kinds of hacks.
I guess there is going to be tons of actions that we did throughout these workshops that you have other kind of ways to do that. So it would be nice if you jump like this and share your thoughts, because also this leads to an upgrade or update in the following sessions maybe.
Yeah.
So thank you for the contribution.
Yeah, I mean, we learn a lot as well from you guys.
Yeah. So other than that, I think everyone is seems quite nice, at least since no one is saying anything negative. And
yeah, the issue was 2, by the way.
Okay.
It is resolved now. Yeah.
Okay. Cool.
All right. Okay, so let's keep going. One of the things that I realized here is that I didn't name this input, and I want to make this a group, right? So this is a domain. So I'm going to search for the domain component, input, and name this speed. Right click, text, put it in here. One of the things you can do also in Rhino 6 is you just double click on the wire, right? And then you create a relay. The problem is I never found a good way to use the relay, because usually I work, if you click on this green thing here, right? Only draw preview geometry for selected objects. If you click on that, then everything you click is going to show up on the screen. So this is nice for debugging stuff. The problem is if you click on the relay button, you actually don't get a preview, which kind of makes it a bit useless, because instead of the relay button, I can just have the actual point. And then if I click on it, I know what it is, right? So I personally never use a relay. I mean, if you double click, if you right click, you can close the relay, but if you right click here, you can also disable it. So I never use relays. I personally don't recommend it, but if you guys use it, then go ahead. Okay, so here I have a nice little random vector generator. I will press Ctrl G, I will group it, and I will color it in dark blue because that's kind of what I did in the presentation, and right click here and give it a name. So I say randomly generate move. My output is the moving stuff. Okay, now I want to connect this to the loop, and I want to see if it's working, right? If it's randomly moving all of the particles. So what I need to do with the loop is I need to pass certain data over and over again to the beginning of the loop. So if I click the plus button here, I get D1. The first data that I want to pass is the stuck particle. So I'm going to write S particle. The second data I want to pass is walking particle. My stuck particle is first of all going to be this point. And then my walking particle is going to be these points that I generated on this circle. W particle. I want to rename this as well, just so it's clear. S particle, W particle. And then here, loop end. Basically, it's crying right now. It's red. And the reason is because loop start and loop end must have the same amount of data streams, right? So here I have to press plus. I have to rename it S particle. Particle. It's a bit tedious, but you don't have to rename it as long as you know what you're doing. It's fine. Particle, W particle. Now, I need to get these W particles not from the beginning, but from the loop itself, right? So this is one advantage of having this kind of structure. I know what the input is. I just change the input. Done. The particle speed is not changing throughout the loop, so I can take it from the outside. These things are going to change throughout the simulation. The particle speed is not going to change, so that's coming from the outside. And finally, at the end, after I move the particles, let's keep this here for now, just so we finish debugging this. So what we get after we move the particles here is we get points. And let's have a panel. The thing is, we see that these points are still in branches, right? It's still grafted. I don't want this anymore. I want these points as a list. So I'm going to right click and I'm going to flatten them. And when I flatten them, they become a list again. And that's good because we had them entering as a list and now we have them coming out as a list. In reality, it makes sense to put this flatten also inside the function, because then the input and the output of the functions are congruent, right? We want to have the same input, same style of input, which is a list, and we want to have the same style of output, so that if anyone else uses our code and we give them this, they're not confused about, wow, why is it suddenly getting grafted inside the function, right? So I'm going to click on this. I'm going to alt click, copy it all the way to the end, take this point and plug it in here. So now I know that my walking particles are coming out. Yes? No? Okay. I'm going to group this and I'm going to make it blue again. Because, oh, sorry, these are red, right? We said the walking particles are red, so I'm going to make it red. So I know these are my walking particles, and then I'm going to plug it in walking particles. Before I do anything though, save your file, just in case. Loops get a bit crazy sometimes, especially if you have problems with the grafting, with the lists and stuff, and they might crash your Rhino, especially because we're in the debugging stage, so save your file. I'm just going to save it on desktop and I'm going to call it DLA workshop. Okay, there's something in the chat. I agree, okay. Okay, let's try plugging in and see what happens. Nothing. because this isn't plugged in. So let's plug this in. Nothing happens. Okay, great. We also want to pass the S particle. So again, I'm going to click on this and I'm going to press Alt and I get a new curve or a new point. Right click on it, rename it S particles, connect it to S. I will again Alt click, get a new one, connect it to here. And I have it here at the end. S particles, group it, make it blue. Great.
Sorry, can you explain again loop start and loop and inputs and outputs?
Yes.
Thank you.
So, oops, sorry. So this loop start and loop end, basically what it does is you input a W particle and an S particle, right? And then here, it will take this S particle, do something to it in the loop, and then you put it back in here to the S particle. And this loop end collects the changed S particle. In the next iteration, it will give this S particle back to here. So every time the loop runs, the S particle will be different, right? And that's why the number of inputs have to be exactly the same as the number of outputs, because otherwise it has trouble. Like if you have more here, then it doesn't know where to get this data from, because it also doesn't know where to pass it, right? You can't go from D2 to loop start because loop start doesn't have the ability to take a D2. So that's why you have to have the same number of inputs and outputs. Does that answer? Okay. While we're here, let's also put a panel to the counter. And let's also put some more inputs here before we start the loop. So for trigger, we want to have a button. So we look for button. Every time we press the button, it's going to run the loop. Okay, it stopped crying. That's good. Now the number of repeats. I want a slider from 0 to I don't know, 0 to 1000, let's say. If you just write 0 to 1000, you get a slider from 0 to 1000. And then I want to set this to 10, just so that we don't run forever right now. We don't know what's going to happen once we plug this in. So let's keep it at this stage quite simple. And now all I need to do is to plug in S particle and W particle. I'm going to save again. Okay. Let's see, I'm also really excited because you don't always get to start a loop from scratch. So let's see what happens. Okay, S particle goes in, W particle goes in. Okay, something happened. We didn't get to see it. The counter went up to 10, which means that it ran for 10 times. That's great. I'm going to press this green button again, right? Only draw preview geometry for selected objects. So now I get to see everything that is white. This is going to be inside a function. So I want to turn everything here off. And I want to turn this guy on, W particles. Okay. This loop end, I also want to turn off. Actually, wait, let's see. Does it work like this? Yes, perfect. Okay, so keep the loop end turned on, as in display on. And loop start, keep it off. Everything else we can keep off. So now we get to see the stuck particle, the S particle, and the W particle. If you press the button, what happens? They all suddenly move, right? In a certain direction. In one random vector direction. So if I increase this, they are just separating. And this panel shows you the iteration, right? I'm going to pause here again. Did everyone get to this stage?
Well, I could get to that.
Okay, then I'm going to keep going. We have our nice little loop. It's working without problems. I'm going to save. I have autosave turned off, I believe. So if you have autosave turned off, keep saving and actually don't have autosave turned off. That's also an important point. Yeah. The problem with autosave is that if your Grasshopper file gets really big, every time you do something, it takes like half a second to save. So that's why I turn it off sometimes. So what's the problem here? It's not doing what I wanted to do, right? It's not changing the random number. Every time it runs, it's using the same vectors because we get the same random vector, and this random function is not changing. It's just outputting the same random numbers every time. Right now we're debugging the code. So what I'm going to do is I'm going to provide a seed that's changing every iteration. What a seed is basically the computer can't generate actual random numbers. It runs an algorithm, but it takes a seed as its initial point, and then each different seed will generate you a different set of random numbers. So what I need to do is I need to generate a different seed with every time the loop is running, right? So an easy way to do that is to just plug in the counter. We know the counter changes every single time it runs, right? So I just plug in the counter value to the seed. And I run again. And now it's more like what we want. Some of you might have noticed that this is not actually a random simulation, because every time it runs, it's using the same exact seeds for every iteration, right? So it looks kind of random, but it's not really random. But right now, for our purposes, that's okay. That's what we want. We're going to change that later on. And I don't actually know why some of these points are always having the same pattern, right? Look at this one, for example. It just keeps going. It's kind of fun to watch, actually, some of them. They're like, they kind of like have their own personalities. One of the things that I want to do here is I have this function and I have an input here that's randomly coming in, and this is going to cause me problems later on because I'm not going to know where this input is coming from, right? So what I'm going to do is I'm going to create a number component. I'm going to right click it, name it iteration, right click, make it to text. I know what it is. I will plug it to iteration, the panel, and I will plug this in to the seed. So it's the same thing, right? But now I know what this is. I can click on this iteration, right click on the group, and click add to group. Add to group. And now this is my function. It has 3 inputs. It has 1 output. It knows exactly what it's doing. It randomly generates move vector, moves, right? Let's create some space. Okay. This is the first checkpoint. So if you were able to get this far, great. If you weren't able to get this far, great. You can just continue from the checkpoint. And the checkpoint is, let's see, DLA checkpoint 1, move particles, right? I'll give a 2-minute pause for any questions, any comments, anything you can improve on.
I think I have a problem with anemone, the plugin. Bummer.
The plugin itself.
Yes. I can't even open the checkpoint file.
Okay.
I only have, yeah, it's, I'm gonna check the problem in one of our breaks or at the end of the day.
Okay. Do you have this tab, the anemone tab?
Yes, but I only have loop start and loop end, and when I zoom in, I cannot put the plus signs. I cannot change anything. So when you wrote S particle, W particle,
Okay.
I was not able to do it. So from that point on, I switched to watching mode.
You might have an older version of anemone.
No,
No?
anyways.
Okay.
Maybe as we said at the end of today, on the drive we can share our versions or find them at least to match what we have here. Although it still might be different because some of you have Rhino 7, some of you have Rhino 6. So we try to do our best in order to match everything. Yeah.
Okay. Yeah. Okay. Maybe then at the end of the day, I mean, we only have 1 hour left, right?
Yes, I think today we said it's going to be 3 hours.
Okay.
Yeah, so we have an hour. If you want, by the way, are we planning to have another break or what do you think?
We could have a 5 minute. I'm okay. I can keep going, but let's ask the chat.
So yeah, do you guys prefer another small break for 5 minutes just for needs?
No one wants a break.
Maybe it would be good to take break now, a really small one, because otherwise then we have an hour of
Yeah.
Okay.
Exactly. So okay, let's call it a 5 minutes break then, and then we're gonna be here.
Okay, let's do it. All right, so 5 past, or let's say 6 past, 7 past.
So just to light up a conversation, when you're doing this DLA algorithm in 3D, does the whole operation is different what you down from here?
No, actually, it's exactly the same, the algorithm. The only difference is you have a Z component.
Okay.
Pretty much. I mean, of course, like there's probably some other minor differences, but if you just add a Z component, it suddenly becomes 3D. And here we're going to use, for example, to figure out if they're close to each other, we're going to use circle boundary. In 3D, you just use a sphere boundary. Here we use a circle to define the initial curves. There we use a sphere. Yeah, I mean, technically, you guys, after you're done watching the workshop, you can just expand it into 3D yourself and just have fun with it. Yeah.
Because it was super interesting example that you showed in the presentation. So I will be definitely also having a look at it and try to make something in 3D. Yeah, I mean,
yeah. So this is basically, if you start, instead of starting with a point, you start with a line, and anything that gets close to the line will get stuck, for example. And then you just make a sphere of particles and you just throw the particles at it until it grows in 3D. Actually, wait a second. I will try to find the 3D print of it.
Right, nice.
Here's this. So it's the 3D print of this, the middle one. And then we had...
For a second, you start sharing screen and we can see it better maybe right now because...
Stop sharing the screen? Okay.
Yeah, for a sec.
Yeah. Wait, what? Stop share. Yeah. So this is what the 3D print looked like. Yeah.
Cool.
May I ask a question?
Yes.
In your introduction, you showed a picture of, I think it was a termite nest.
Yeah.
Or an ant's nest or a termite nest. I don't know.
Yeah.
Do you have any resources on how to implement this with code or with Grasshopper or anything?
No, I can't, not off the top of my head, unfortunately not. I can think about it over today and see if I can think of something that we did previously. I never worked on the termite's nest, but I know some of our classmates did. And maybe I can try to find something, but I can't guarantee it's going to be better than what you find online, unfortunately.
Okay. Thank you.
Are you interested in modeling that as well, the termite nest?
I like the shape. It reminds me of, I forgot the name of that. I think it was a research studio in an architecture school in Spain. I forgot the name, I'm sorry. Who came up with a shape which is quite similar, but I think it was not a termite nest, it was an ant nest.
Okay.
And I really like the porosity of the whole shape, and I eventually would like to model this either in Grasshopper or in Houdini. I don't know anything about Houdini, but I know a bit of Grasshopper, so I would like to try in Grasshopper.
I actually do have a resource for you, but it's not Grasshopper. It is coding.
Yeah, great. That would be great.
Yeah, I have a great resource for you, all of you guys, actually. Now I remembered. Let's go to YouTube. And actually, so our professor, well, our teacher who helped us do this, Long Nguyen, I don't know how to pronounce his last name. He's
Yeah. He has great tutorials on.
Oh, you know it already.
YouTube.
Okay, nice. Yeah. He has this 3-part reject. He has this 3-part tutorial. What is it?
Growth behavior.
Yes, it's a C#.
Yeah, it's the best one.
Yes, exactly. So for all of you, this one is amazing. It's 6 parts. It's like for 12 hours or something. And this one is Visual Studio and stuff like that as well. So it's a bit in depth, like you have to prepare for it. You have to, I'm sure you know if you've done it. I actually tried to do this tutorial like 3 times or so from beginning to end. And I still, I probably need to do it again because I keep forgetting. If you don't use the skills, you always forget. Yeah, but it's very good. But you already know all the resources, it seems. So,
but I think this one is a bit different because it's just a differential growth behavior. But in the case of the nests, the ant nest or the termite nest, I think it's a kind of different behavior. I'm not aware of. So, yeah.
You also know the coding train?
Yeah, of course.
Yeah, okay. I think some of his agent-based stuff can be relevant, but yeah.
And I think also in Barcelona, Yak has a similar study. If I can find, maybe I can share some information as well, because they do those kind of things into reality generally. So there might be some resource there as well. So yeah, we have a material section in the drive, so we can put when we have something for you guys. So later on, you can have a look at it.
Okay, I'm going to continue. So we have our particles, which are quasi-randomly moving around. What's our next step? To see if they're stuck. Now, if we were to try to do this on our own, like using the Grasshopper script, how would we do this? We would go to every particle which is stuck, and we would check what's the distance between this particle and this particle, and then see if it's smaller than this circle radius. And then if it's smaller, then it's stuck, for example, right? And then we would check the distance between these two, see if it's stuck, check distance between these two, see if it's stuck. There's alternative methods to doing this. Of course, you could also make a circle here and see if these guys are in the circle. But at the end of the day, you have to go one by one and you have to check for every single particle. So you make a circle, see if this is in the circle, see if this is in the circle, see if this is in the circle. It's not, you go to the next particle, make a circle, see if it's in the circle, all that stuff. This can take a while. And as we were trying this, I'm not sure if I implemented the fastest algorithm. I mean, there's so many things you can do here, right? But one of the options that you can use is use something called R trees. And it's nice to know what R trees are because there's a lot of use cases for R trees, right? Basically, this is the reason why we wanted you to install the Lunchbox plugin. And it has an R tree component. R trees are used for storing geographical data and searching through geographical data. So there's a lot of companies and everything that we use today uses some form of R tree or some kind of geographical data storage and search system. R tree is one of them. So if you call an Uber and you're here and you want to see what cars are close by, then R tree would be a good option because it will quickly find what cars are close to you. If you're using Google Maps and you want to find groceries that's close to you, it will find it quickly for you. If you're using Tinder and you want to find the girls who are close to you or guys, then it's going to do that for you. And these apps use this system. Basically, what the system is it divides these points into rectangular areas, right? And then it gets progressively smaller. So basically, This is kind of an example that I drew. I don't know exactly how it's dividing it. I don't know the details of this algorithm, but it has R1, which is this big rectangle. It has R2, which is this big rectangle. And then inside R1, it has R3 and R4 and etc. And then it creates this kind of hierarchical structure. That's why it's called a tree. And the R stands for rectangle, right? So rectangle trees. And basically, if I have a blue point in R5, I know my blue point is in R5, and I want to search which point is close to the blue point, right? If I know my blue point is in R5, I don't need to search R3 or R4 or R6. So instead of checking all of these points, it reduces my computational time to just checking three points instead of all of these other points. So I eliminated R1. So this part of the tree is completely gone now. I'm only in this part. And then it checks, okay, R6 is irrelevant for you. So R6 goes away. And now I'm in R5 and I only check 3 points. And this significantly increases the speed of the simulation, especially if you're going 3D. So even in 2D, it makes a big difference because we're going to use VLSA and we're going to need to run a lot of iterations. So it helps a lot if it is, if it's able to do this, right? Okay, so this is how we're going to figure out if it's if the particles are stuck or not. Now let's go back into Grasshopper. Okay. So doing the implementation of this, I might also get a bit confused. So excuse me, since trying to do this live is also slightly, I have to explain my thinking as well. So we have here W particles and S particles, right? I'm going to alt click, copy this, alt click, copy this. And I'm going to make a new function. I idealize a new function over here, right? So the way this R3 function works is if you go to Lunchbox, where is the R3 again? Let's see, if I do R3, create R3, right? If you search for R3, you get this, create R3. Let's see where it is. It's in utilities, create R3. I want to create an R3 from all of my wandering particles. So the red ones. And now I have an R3, a points-based R3 with 150 points, right? So this is this rectangular system. It creates it, we don't see it, it does it behind the background. This is the beauty of Grasshopper. I don't need to know how it's doing it, and I don't actually know how it's doing it. It's fine. Then we need to search for these S particles if they're close to the W particles, right? So how am I going to do that? I go to utilities and I see what options I have here. R3 points in range. So this is very nice because then I can just search within a circle. So I take this, put it here. It wants my R3, I put in my R3. It wants my search points. So I want to search from my stuck points. So I'm going to enter this here. And then it's asking for a search distance, right? So what's my search distance? We haven't defined this yet, so I'm going to define it. I'm going to have a slider. I want it from 3 to 6 again. You just write 3 to 6, it comes up, number slider, rename it, stick radius. And then I will create a number component, plug this in, stick radius. And I put it here. Because this is going to be inside the loop, it will be nice to have everything that's going into the loop in a nice organized fashion, right? So I'm going to keep this stick radius here as an input to my loop, as an input to my DLA algorithm. And then I will alt click, copy it, do this. And now I have it copied, taking it from here to here. And I take it all the way here into my next function. You might find it a bit annoying that I keep doing this. I keep taking it, I keep alt clicking it and doing this. Is there no better way to do it? You might use relay, we talked about that. I just like it like this because it makes everything clearer, and it's more important to me that the code is clearer in the long run than it is to do it fast, because if you want to revisit the code, you're going to slow down anyway once you don't understand what you did. So it helps to do this. Now my search distance is stick radius. It's going. Okay. I'm going to save here just in case. And then I have indices within range and points within range. So it didn't find any points within the range, and it didn't find anything inside the range. So why not? Well, because there's nothing in range, right? It makes sense. Let's try to run this again. Does anything go in range? It's a bit hard to see here, right? But at some point, things should be coming into range. We can figure this out later. What I want to do, though, is to increase the stick radius just to make sure that something happens, because 3 is a bit small, right? So I want maybe, let's say 5. Okay, let's stop this guy. I'm going to reduce this. Okay. So now, how should we do this? I'm thinking about a way to visualize what I'm doing here. It's going to be difficult if we don't see any particles that are close, right? So maybe we can reduce this circle all the way down here and lower the iteration to 30 or something like that. Run. Okay. If you do something like this, you actually get points which are close to the center, right? So ideally, yes. So now you see the archery found some points. Is this part clear? What I'm doing is basically a form of debugging. The options that I had before wasn't allowing me to see what was going on. So I changed the options. I made everything simpler. I made the sticking radius bigger to make sure some particles got stuck. I reduced my circle size to much smaller to make sure that I could see some particles which are getting stuck. And then this helped me to figure out that I have some stuck particles, right? I hope that's clear. So I'm going to continue. Now I have some points within a range, and I can see them. When I click on this, I see some of the points are highlighted in green, which makes sense, right? So it's a circle that's containing these points. Now what I need to do is I need to change, I need to move these points from W particles to S particles, because now they're not W anymore. They should be S, right? They should be stuck. So the way I can do this is I can take the indices and I can make a set out of them. There's a component create set. The reason why I'm creating set and not just taking all of these indices is because it might so happen that a point might be close to 2 stuck points at the same time. So there might be, 34, 6, 34, 34, 34, 6, for example, in which case I only need one of these guys. So this is what the create set component does. It just takes all the different values and it creates a set out of them. So now I know that if I have repeating values, I don't need to worry about it because I have all of them once in this set, right? Also, maybe to clarify, what this indices means is that in the R tree, the 34th point is close. The 104th point is also close, and all of these ones are close. So these are the ones that I'm looking for, right? So if I create a list item, I take it, I take the particles as the list, and I take the indices, the set. What I should have are these points which are close. And I do have that because they're green, right? You can see it. So what I need to do now is to make sure to add to the S particles these new particles. So how can I do that? I'm just going to go merge. 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 Nice. When I'm using merge, it's somewhat of a habit to right click and flatten these. I do this because merge is really annoying when you have inputs which are different tree structures. If I know that my end product is going to be a list, I just flatten them here. And for example, if I graphed this and I don't flatten, then you see what I get? I get a tree with completely weird data structures. I have 1, 0, and then I have 1, 0, 0, 0, for example. And this will ruin everything. And at this stage, I'm just going to avoid this. And I'm going to say, whatever happens to this input, just flatten it. And I want to get a list. And now my result is all of these points. They're all stuck. It's nice. The next one I want to do is I want to remove these points from the walking particles, right? How can I do that? There's another component. It's called call index. What this does is it just removes these indices from the list, right? So again, I take the list, I take this indices, and I have all of the points which are lying outside. And these red ones are not ones that I want, right? So what happened here is if I just copy these guys again, I click both of them, alt click, move all of them over here, and I have copied S particles and W particles. I take this list, put it into W, I take this list, put in the S, and this is what I want my function to do, right? I'm going to save. When I was doing this on my own, I crashed my computer a few times, so I don't want the same thing to happen to you. What happens is that if there are multiple particles, what this R tree does is it gives the indices in a tree structure. And I don't want indices within this tree structure. I want all of the indices flattened in a list. So please right click here and press flatten in the indices within range. This is just a tip so that we don't crash our computers later, because this created a problem with me. And yeah, let's just to avoid problems happening later on. Okay, and if we have done this, now we have our nice little function. I'm going to go group, right click, and give it a color. What was it, this one? What do I have? Yes, it's blue, it's light blue. So I'm going to give it light blue again. And I'm going to name it. What should we name it? Check if particles are stuck, stick them. And now I'm going to save again. I still don't know if it's going to work or not, right? So we might have to debug this. But if I put this S particles inside here and the W particles inside here, okay, nothing happened. I'm going to click all of this, middle mouse button, disable preview. Okay, moment of truth. I'm going to run. Okay. So we can't see what's going on here. It's very unclear, right? Until now, are there any questions? Now I'm going to work on displaying this in a way that's nice. Okay. So instead of visualizing this component, this loop end, I'm going to disable this. These outputs are outputting to me always these S particles and W particles. So I'm going to again click these. This time Control C, Control V, and I copy them. The reason why I did Control C and Control V and not Alt click is because if I do Alt click, I don't copy the groups, right? So this is also a quick tip. The groups are not copied unless you unless you Control C, Control V. Alt only copies the components. Small, whatever, small tip, doesn't matter. You can just regroup them at the end. I'm going to plug this in here, S particle, W particles. Then I'm going to use Grasshopper's own display components to display them in color, right? What was it called? Display? Was it? I forget what it's called. Custom preview, I think it was, wasn't it? Yes, custom preview. So this custom preview, here I can define better in what color these particles are going to look. So I'm going to plug this in here, geometry, and I see them in pink. And I take this guy and I see this in pink as well. It says material, so I'm going to change the material here to see it in different colors. So I'm going to say color. I don't get what I want. Okay, now I get what I want because it's with a U, because they are British, apparently. Which one do we want? It doesn't matter, just we can take RGB. Oh no, it does matter. This is wrong. Color picker. Yes, we need the color picker. So search for color picker. And here we can just quickly define our colors. So I plug it in. I change the values. The stock particles, we said we're going to make them blue. So I'm going to make them a nice shade of blue. And the walking particles, again, I'm going to Alt click, put it here, plug it in, and I'm going to make them red. And now I have this display. I'm going to group this, and I'm going to right click and say display. It's getting a bit annoying to group and name the groups. So instead, I'm going to use scribble here. If you write scribble, you get this guy. We do what it says, and then we say display. Make the size a bit bigger. Right click on the group and press add to group. And it is here. Now I don't need to worry about this. This can go away. I will save. And I will run. This is exactly what I want. Any questions?
I have a question.
Mm-hmm.
I mean that it's like a Python loop, and each data stores for each loops. And for example, setX does setX like append in Python coding?
I didn't understand your question. Which one is append you were saying?
Set, create set. I mean, for each loop, it store data and update them. It's because it's like looping in Python coding.
Yeah. Yes. So the append, what I'm using here as the append is this merge, technically, because I have my previously stuck particles. So I'm going to I have my previously stuck particles, and I have a new particle that gets added to the list, right? So basically it's the same as saying append this item to this list, and what's doing it is the merge. So I merge them, and it's basically exactly the same. It just puts it at the end of the list. D1 plus D2 gives you this append. And this one, the call index, it's exactly the opposite. I think in Python it's called pop. Am I remembering this correctly? It's been a while. If you write pop, you can take out stuff from the list.
Okay.
That answers your question, right?
Yeah, exactly.
Okay. Yeah, so it is exactly, and that's the beauty of it, right? You can, once you know the kind of the main functions you need, you can just bring this to coding. If you know any coding, you can use the same algorithm. You can even use R trees with Python. And I think you just do import R tree. It's quite simple, actually. Let me see if I have here. I think Grasshopper already comes with that. No, I don't have it here. But it comes with the functionality of R tree, so you can use it. It's a bit annoying though. You have to like look through the documentations. It took me ages to understand how R trees work in Python. Here it's much simpler. Okay, nice. So now I'm going to go back to my original input values. So I'm going to write here, what was it, 35? Make the circle bigger. Number of moving particles, it was 150. We know the loop works, so we can just increase this. Let's increase to 300. Particle speed, let's make it 4. And the stick radius, let's make it slower to see what happens, right? Let's go 3. Let's increase the iterations. Oh, okay, there's a problem here. I'm not seeing anything. I need to press the screen button again. Yes, now I see it. I increase the slider to 1000 and I press the button again. Is it doing what I want? Yeah. It's doing what I want. Okay. You will notice that every time I press the button, the same exact structure is going to appear. Why is that? Because the numbers that we're generating, the random numbers, are not really random, right? It always uses the same numbers as the seed. We're going to fix that. Don't worry about it. We can do it tomorrow. We have 20 minutes. Let's use that time to create an end condition for the loop. Here, there's an exit entry, right? Right now, it's set to false. If I set this to true, it's going to finish the loop. When we're using Valase, we're not going to be able to see what's happening inside the loop. Let's stop this. It's a bit annoying. Reduce this. Actually, if you double click on the loop, you can also stop it, I believe, but I just do this. So when we're using Valase, we're not going to be able to see this happening. So we're not going to know if the loop is taking really long or you know, what's the hang up. So I'm going to put a slider here, make it 200, enter, and right click and call it maximum number of particles. Again, I'm going to create a number component, input, right click, max of particles, right click, make it text. Great. Then again, alt click, copy it, take it all the way here. Now I need to write something small to make sure that if the maximum number of particles, or if the sticking particles are bigger than the maximum number of particles, I need to get a true, right? And I need to exit the loop. So I just go bigger than. The number of S particles need to be bigger than the maximum number of particles, right? So I'm going to, again, length, list length. If this number is bigger than this number, then I need to get a true. Right now it's false. That's fine. Is it false? Let's see, how many numbers do we have? We have 155, so it's true. It is false. If I put this to 150, I go back and I check if it's true. It's true. Great. So I'm going to make this another group. Change the color, whatever. Exit condition. And I will plug this true into the exit. Let's see if it works. I'm going to make it very small just to see if it works. Press the button. Let's see. I'll make the iteration bigger just in case. And it should somehow stop pretty soon. Yes, it stopped. How many points do I have? 80. It's bigger than 79, so it stopped. Okay. That's good. We have the exit condition. Now we can have we can try to work with these wires, the display options. This is something that the Grasshopper makers wanted us to use. They say this, they say between every function, you should right click, go on wire display, and go on faint. And this prevents you from having crazy wires everywhere, right? So I go right click. I mean, you don't have to do this. I'm just showing for good practice, faint, faint. Here as well, they're coming from the input. I can just go to faint so that it makes visually my life a bit easier. Faint, faint. Okay. We have 20 minutes. Let's see what our next step is. Our next step is to increase efficiency, right? Let's quickly talk about this and then go into the Q&A. I think that's pretty much the time we have. So the next thing we need to do is to stop particles from getting too far away. Now, one of the problems you notice is that once a particle goes all the way out here, there's no way to bring it back, right? It's not going to get stuck. It's not going to do anything. It's just going to keep wandering around and it's going to be useless. So the next step we're going to do tomorrow is to define another circle, which is going to pull back these particles and add them back into the mix. And that will also increase the efficiency of our system. Okay, I think this is a good time to stop and go with the Q&A, right, Ulf?
Yes, yes, I agree.
Okay.
Depending on our time tomorrow, we can arrange our divisions. And for today, I think we have already seen a lot. We don't want to scare anyone anymore.
Right now, this version of the code is a checkpoint. It is, I believe, stick particles. Yes, 2. We don't have this much to go. Don't worry. Like, we did half of the work, so this is going to be hopefully a bit faster. This clustering is just very quick anyway. So yes, we're pretty much halfway there. We just need a few tweaks here and there to make it more efficient, and then we're going to be ready.
So ideally, could everyone come till here, what we have on the screen? I mean, do you see the same thing that we have in the screen also in your computers? Or was it too fast and you couldn't catch and gave up at some point? It would be nice to have some feedbacks. Yeah, also, sure. It would shape on the next days of our workshop.
No one is saying anything. Was it at least like, are there good parts about it? That's what we can also have comments on that.
Okay, at least there is no negative comment as well.
Yes, okay, I'll take that.
Okay, thank you. We have a feedback and Sana says the speed was great.
Nice, good to hear. I'm gonna stop sharing for now.
Thanks, Piyush.
Any questions?
Yes, we are gonna upload it, but it takes a bit of time to optimize the video, and then also depending on our upload time, I don't know when it's gonna end, but definitely you're gonna get the records. Don't worry about it.
Ayman writes, okay, sorry, I didn't introduce myself because I have a flu and my voice is horrible. Actually, I barely can speak, but it was thanks a lot. It was super good. Thank you. Yeah, it's no problem. If you can't speak, then get well. I don't know what time zone you guys are in. I hope it's okay. And even, I mean, we also thought about the Saturday and Sunday. I hope that's okay for you guys as well, because we're both working, so we can't do this during the week. I think most of the workshops were during the week.
Yeah, thank you for this great dedication.
Yes.
That you are leaving your weekends for this workshop.
Yes. Yes, exactly. We still have 10 minutes. I'm going to think about maybe certain things that I can talk about still without getting into the next steps. Maybe we can talk a little bit about the beginning part of what I talked about. I'm curious how many of you in your studies actually know, for example, Michael Batty, know Hillier and Hansen, because in the last 2 or 3 years, I really got interested in architecture theory, and these writers are really doing really cool works or have done really cool works. And I feel like most of the architects have not really seen or heard of them unless they're interested in this field. So I'm curious if you know them, or if you don't know them, if you've heard of them.
I do know Bill Hillier, or Hillier, I don't know how to pronounce it, because of his work on combinatorics, permutations. There is a chapter in one of his books, I forgot the name, sorry, I forgot everything, called Is Architecture an Ars Combinatoria? And it's all about combination. And I came across his work while reading a book from Kostas Terzidis, I don't know how to pronounce, on combinations. And I know he is pretty much the guy who, tell me if I'm wrong, but I think he is the guy who basically created the field of space syntax, or maybe I'm wrong, but I think a significant part of his work is being used in space syntax. That's pretty much what I know.
Yeah, actually, I believe Hillier and Hansen were the ones who first talked about space syntax. I know Terzidis is doing a lot of work on it, but I think actually the first book on space syntax was written by Hillier. But I might be wrong as well. I mean, we can check that. Terzidis, I believe, is a younger researcher, no?
Oh yeah, I was talking, sorry, I was talking about the Hillier, of course.
Okay. Yeah.
Also, Radwan, another subject is about the exhibition. Do you think we should talk about it right now, or in the next day? Maybe we can explain about it.
We can talk about it now because we have time.
So I think it was on the 5th of July, right? The submission. Yeah. So it's a bit also information to encourage you about producing something. At the end of the workshop, we are going to have an exhibition as well, which is going to be consisting from all the workshops within the theme of One Planet of Digital Futures 2022 Summer Workshop Series. So at the end of our workshop series as well, what we have, I mean, as a product that comes from you guys, we're going to submit them on a virtual world, like in a metaverse platform, I guess. They are going to be exhibited. So it would be nice for you to also have your own generations at the end, and you can just submit them on the Drive folder that we share with you. We're going to open a folder there as well. So there is no like a specific format or anything. We're just going to show how to create an urban fabric, and then you're free to do anything that's up to your imagination. Like you can create an illustration with the generation that you created, or you can make a render. It really depends what artistic skills you have, or you can just take a screenshot and upload it. It doesn't matter. So just have fun, and then it could be interesting for you to have that kind of exhibition for you as well.
Yeah.
Okay.
If you believe in the metaverse.
That's another subject, but
Yeah.
Okay, we already have a thumbs up.
Nice. Yeah, I never did any metaverse stuff until now. I've never been into a metaverse party or anything because it just always lags. It never works for me. So, but hopefully this one works.
Suddenly someone can cut our broadcast here and
you can cut this part.
Okay.
All right. I think we can call it a day, no?
Yeah, sure. If anyone has any additional comments, otherwise we can end it, I guess. Cool.
All right. Thank you guys a lot for being here. Yeah, I had a lot of fun doing it, and let's see. I mean, tomorrow is also exciting. Yeah, see you guys tomorrow.
Okay. See you guys. Bye bye.